Today we will focus on the reaction rate. So that's the rate at which the reactant A is converted in a product P. The reaction rate determines the required volume of the reactor tank. And note, the larger the volume of the reactor, the higher the investment cost will be. In this video, you will learn how the reaction rate influences the required volume of the tank. You will also see how the reaction rate depends on the concentration of reactant if a chemical catalyst, an enzyme, or a microorganism is used. Remember that the required volume of the tank can be determined from mass balances. As accumulation is in minus out plus reaction. In the mass balance, all terms will be in moles per second. Here you see the tank filled with medium. And inside the tank you also see the catalyst. A homogeneous reaction takes place. Under steady state conditions, the flow of medium with a high concentration of reactant A enters. Inside the tank there's a reaction going on, and a flow of medium with the product and some remaining reactant leaves the tank at the same concentration of the contents of the medium inside the reactor itself. It's an ideally mixed medium. The overall reaction rate can be found by multiplying the reaction rate per volume by the total volume of your tank. So if you know what goes in and you know how much reactant you want to convert, you should know how much reactant is leaving, and if you know the reaction rate per volume, you are able to calculate the required volume of the tank. But how do we know the reaction rate per volume? This depends on the type of reaction and how it is catalyzed. The simplest reaction is the zero-order conversion of reactor A to product P, catalyzed by a chemical catalyst. Zero order means that no matter what the concentration of reactant A, what is available, the rate at which it's converted is constant. The rate constant Ko has the same units as the reaction rate Ra, so moles per cubic meter per second. But more often, you will see that the more reactant A, the higher the reaction at which it is converted. Then the reaction follows first order kinetics with rate constant K1. Note that the rate constant K1 is expressed in the unit per second. You could also have chosen an enzyme for the conversion of reactant A. Enzymes often follow Michaelis-Menten kinetics. The reaction rate initially increases linearly with the concentration of your reactant, but gradually you see that the reaction rate levels off until a maximum reaction rate is reached. When looking at the Michaelis-Menten equation, the term Vmax stands for the maximum enzymatic activity. If you add more grams of enzyme, Vmax will increase with the rate constant Ke. This enzymatic rate constant is expressed in moles of A that are converted per gram of active enzyme per second. The Michaelis-Menten constant Km depicts the concentration of reactant needed to reach half of μmax, the maximum enzyme activity. If the concentration of reactant A is very high, let's say 10 times higher than the Km value, the enzyme works at its maximum rate. Increasing the concentration of reactant at that point does not result in higher rates, and the enzyme conversion follows zero-order kinetics. It can also happen that you work with a very low concentration of reactant A, let's say 10 times lower than the Km value. In that case, the reaction rate is linearly dependent on the reactant concentration, and the enzymatic conversion follows first-order kinetics. Now let's have a look at the reaction kinetics how the reaction kinetics works out if you choose a microorganism for the conversion of reactant A. Often the formation of product is associated with the growth of the microorganism itself. For example, in an anaerobic fermentation with yeast, sugars are converted into ethanol, while new cells are formed at the same time. So per amount of cells that are formed, you will find an amount of ethanol that is produced, and this amount is the yield of product per amount of cells, YPX. The microorganisms grow with a specific growth rate mu. In many cases, this growth rate follows Monod kinetics, quite similar to the Michaelis-Menten kinetics for enzyme reactions. At high substrate concentrations, the maximum specific growth rate μmax is reached. And the specific growth rate at these substrate concentration is constant, and you might also say that it follows zero-order kinetics. The concentration can also be very low, let's say lower than 10 times the Monod constant Ks. At these low concentrations, the specific growth rate increases linearly with the substrate concentration, like a first-order reaction. Now let us use this approach to determine how we can increase reaction rates and thus decrease the reaction volume. We'll first focus on the situation where you have high reactant or substrate concentrations. In this case, the reaction rate can only be increased by increasing the concentration of enzymes or the concentration of the microbial cells. If you're working at a low concentration of reactant or substrate, you can have two options. You can, of course, again use more enzymes or microbial cells, but you could also increase the concentration of reactant or substrate. All in all, you may have recognized that complex kinetics, such as enzyme kinetics following Michaelis-Menten kinetics, or the Monod kinetics for the growth of microorganisms, can be simplified to either zero-order or first-order kinetics. Let us thus assume whatever catalyst we use to convert a reactant A to a reactant B, that the reaction follows either zero-order or first-order kinetics. The reaction rate equation can now be entered in the mass balance. And with that, you're able to calculate the required volume of a conversion tank. See you next time.